Hello students! In this video we are going to discuss the guided study for learning target AD3, the second derivative test. In this learning target we are going to use the second derivative test to locate possible points of inflection and determine intervals of concavity of a function. So to start, let's just make a note that the second derivative test introduces us to the concept of concavity. And we're going to say that points where concavity changes. So if concavity goes from concave up to concave down, or concave down to concave up, we're going to call that a point of inflection. And don't worry too much right now if you don't know exactly what concavity is. We're going to illustrate that in an example. To start, I want to get the definitions written. So let's define what it means for something to be concave up based on the first derivative. If we have a function that is differentiable and we want to know its concavity, we're actually going to take the first derivative of the first derivative. So if the first derivative is increasing, so if f prime is increasing, then that means f double prime must be greater than 0. Then we're going to say the function is concave up. And I'll show you visually exactly what this is in a moment. For now though, just remember, for concavity, we are looking at the increasing, decreasing behavior of f prime. If the first derivative of a function is decreasing, in that case, f double prime would be less than 0. Then we're going to say that a function is concave down. Okay, and remember what I'm looking at here. I'm looking at the sign of f prime to determine if f prime, let me say that again. I'm looking at the sign of f double prime to see if f prime is increasing. Just like I looked at the sign of f prime to see if f was increasing, I'm just kind of taking it up one step. I'm looking at the derivative of the derivative and its sign to determine the behavior of f prime, which then gives us information about the concavity of the function f. Now, the test for concavity isn't actually called the second derivative test, but I personally kind of use this interchangeably. Technically, the second derivative test is something a little bit different. We'll talk about it in class, but for now, I'm okay with you calling the test for concavity the second derivative test. I kind of use them interchangeably. The second derivative test technically gives us information about the extrema of functions, but we'll test for concavity, and we're going to have a function f, just like we had from before, and we're going to say that that function is at least twice differentiable on an interval. That just means we can take its second derivative. And I'm going to write very similar to what I have above, but in a different way. If f double prime of x, if the second derivative is positive, then f is concave up. And what that also means is f prime is increasing. So the graph of the first derivative has an increasing behavior. And then likewise, if f double prime is less than 0, f of x is concave down. And just note that if f double prime of x is less than 0, then what that actually means is f prime is decreasing. And then by definition, if concavity changes around a critical point, and you can find these possible points of inflection by solving f double prime equals 0. So you'll find those a values the same exact way we found the extrema, possible extrema. That's going to be an inflection point. So we're going to have an inflection point if the concavity behavior changes across A, and we're going to test the second derivative to do that, which is again why the test for concavity and the second derivative test I end up using interchangeably, but technically they're not. Now, in order to visualize what concavity is, I'm going to look at this function, f of x equals x cubed. And visually I'm going to say this, and I'm going to prove it to you in a second. This portion of the graph, negative infinity to 0, is concave down. So what we're expecting to see is 0 is a possible point of inflection, and f double prime is negative on the interval negative infinity to 0. And likewise, on 0 to infinity, f of x, so x cubed, is concave up. So look at the picture there. We see a curvy green line here that is oriented upward. Go ahead and add x cubed here since that's the function that we're talking about. And again, just note down, up. To show this, we're going to take f prime, which is 3x squared. Note that f prime equals 0 when x equals 0. We can perform the first derivative test on this point 0. When we perform the first derivative test, we're going to test f prime at -1. But notice that this is x squared. This is 3 times x squared. So regardless of x, regardless of the test point, -1 or 1, f prime is positive. So as we see, this function is increasing across the critical point. Therefore, the first derivative test is inconclusive. So this is where the second derivative, which is 6 times x, comes into play. 6x equals 0 when x equals 0. This is called a possible point of inflection until we prove it's a point of inflection, and it is. Okay, so this was the sign diagram for the first derivative test. This is going to be a similar method. We're going to make a sign diagram for the second derivative test. Again, technically it's the test for concavity, but we're testing the second derivative. We're testing f double prime at -1 and f double prime at 1. Just like before, we pick test points on the intervals. F double prime at -1 is -6. F double prime at +1 is +6. So we go from concave down to concave up. And this is the notation I like to use. I like to use little curves to indicate concave down versus concave up. So this right here tells us x equals 0 is a point of inflection. And actually, since we're writing a point, we should write it as a coordinate. So 0, 0 is a point of inflection. And f of x is concave up on 0 to infinity and concave down on -infinity to 0. And this is a very basic example. The cubic function is an extremely basic example. I'm only picking this example to show you that this is what concave down looks like, and this is what concave up looks like. Concave up is that curviness kind of oriented upward. Concave down is that curviness kind of oriented downward. So if we consider the function f of x equals x squared, and we find f prime is 2x and f double prime is 2. I picked this one because this second derivative is constant. If the second derivative is constant, then its sign is true for all x, meaning this function is concave up for all x. Right? And you can see that curviness kind of oriented upward. It wouldn't be a bad idea at this point to stop and do the first derivative test. This function is decreasing and then increasing across 0, so it makes it a minimum. And I will say this, and I want you to think about this a little bit. It's not possible for a point to be both a local max, local min, and an inflection point. So if it's an extrema, it's not an inflection point. But if it's an inflection point, it's not an extrema. So let's go back to the example that we did in class. Let's finish this example by classifying the points of inflection. And now based on what we just did, you can see that that point 1 is a point of inflection. This is inflected downward. I don't know if that's a word or not, but this is concave down and this is concave up. And remember when we did this in class, the first derivative test was inconclusive for this point. Go back and review that. Or as you're sitting here right now, practice that again. Make sure that you can get the same conclusions that we got from the first derivative test. In this case, recall that the first derivative was 12x to the third minus 12x squared minus 12x plus 12, making the second derivative, and remember, we learned this a little bit in D4 as well, the second derivative is the first derivative of the first derivative. So we're taking the derivative of that function that was our derivative. We can make this a little easier on ourselves by factoring that 12 out and then taking the derivative of the factored form. This would be 12 times 3x squared minus 2x minus 1. And I'm going to leave the 12 factored out when I set it equal to 0. And now this is a really great time to review factoring. This is a polynomial with a leading coefficient not equal to 1. And this is getting some people on L3 part 1. Okay, to factor this, you need to find factors. So find multiples of A times C that sum to B, where A, B, and C are the following coefficients. So the coefficient of A is 3, the coefficient of B is -2, and the coefficient of C is -1. So we need to find factors of -3 that sum to -2. Well, the only factors of 3 that exist are 3 and 1, or -3 and -1, -3 and +1, or 3 and -1. So let me say that again. 3 and 1 are the factors of 3, but we need it to be negative. So we will exclude 3 and 1, and we will focus on the negative-positive combination. And we want to find which of these two, -3 plus 1 or 3 plus -1, sum to -2, and it's this one. So -3 plus 1 is -2, and -3 times 1 is -3. So these are the factors of 3 that sum to -2. So to factor this, we will expand the middle term using those factors, using those. This is 3x squared minus 3x plus 1x minus 1. And notice that that -3 plus 1 equals that -2. All I'm doing is collapsing it out. I'm taking -2x and I'm writing it as a different sum so that I can group, and we did this in class. If I factor out a 3x here, I'm left with x minus 1. And if I factor out a plus 1 here, I'm left with x minus 1. And that's still all times 12. So because these factors match, we see that these factors, 12 times 3x plus 1 times x minus 1, are the factors of the second derivative. Just like before too, we're going to leave this factored when we test it. But notice that x equals -1/3 and x equals 1 are the possible points of inflection. And what we found is the one value we expected, but there's also another one right about here at x equals -1/3. So to test the second derivative, and again, I'm going to put it in quotes, but we're testing the second derivative, so it's really technically the second derivative test. We're going to put the possible points of inflection on a number line, and we're going to test values in between, always testing 1 if we can. And in this case, F double prime, so this is the key. Remember how I was silly in class and was like, so the test that is the first derivative test, test the what? It tests the first derivative. This is why it matters now. because now we're testing the second derivative. We're calling it the second derivative test. We're testing for concavity. We're testing for points of inflection. So we're going to test the second derivative. We're going to plug these values, -1, 0, and 2, into the second derivative. So what we have for the first test point is 12 times -3 plus 1 times -1 minus 1. So we have 12 times -2 times -2, which is a positive number. So we are concave up here. -2 times -2 is +4 times 12, 48, whatever. I don't need to know the actual value. I just need to know the sign. F double prime at 0 is 12 times 1 times -1. Okay, I just plugged 0 in for x there, so it cancels those x's out, leaving me with +1, -1 as a product. -1 times +1 is negative, times 12 is a positive, which leaves an overall negative. This is -12. You could write the value down. That's perfectly fine with me, as long as you recognize the sign. So on that interval, we are concave down. And you can kind of see concave up, concave down, concave up. Always be looking at the graphs for these, just like before. Then we test that last point, f double prime at 2. This is 12 times 6 plus 1 times 2 minus 1. This is 12 times 7 times 1, which I could calculate. I don't need to. I just need to know the sign so that I can show that it is concave up. You have to show this. So this is the work that you need to show. You must show this work. Once you show this work, you'll draw the conclusions at -1/3 f of -1/3 and at 1 f of 1, there are points of inflection. Please go calculate out these values. I didn't ahead of time, and I'm not going to spend time sitting here while I'm recording this calculating those out, but you need those values because they're points. Okay, we can look at the graph and kind of estimate it. That -1/3 value should be negative, a very small negative number. Go do that right now. And then this one, we can actually see it's probably about 6, but I haven't calculated this out. So you do that. Those are the points of inflection, and on the intervals -infinity to -1/3 and 1 to infinity, f of x is concave up. Okay, I'm looking here at the up U's. They look like little letter U's. They're up, and they're up because they're positive. And on the interval -1/3 to 1, f of x is concave down. Now, we will have 2 big examples we're going to do in class. You can look at the class notes if you'd like to try to get a head start on those. I highly recommend that you do your best with the guided study questions, and then remember, if it says bring your work to class, please bring your work to class. As well as, don't forget, you are finding the critical points for that rational function in the class notes for your exit ticket exercise. And for today's code word, I would like for you guys to please input the animal, a red bird. Again, please make sure you go through and you calculate these values. And do your best on those questions you bring into class, right? Like, genuinely try. If you don't quite get it, that's okay. You're bringing it to class and we can talk about it. You're going to come to class and we are going to not review these notes. You'll have these. I'll post these at the beginning of class, but please make sure that you put some solid practice in before class, because that's all we're going to be doing in class. We'll talk about the formal second derivative test, but in class we are doing examples.